This is the third lecture of chapter 17, which deals with aromaticity and substitution reactions involving aromatic compounds. Of course, we describe those reactions as electrophilic aromatic substitution. So, first, we will do a quick review of aromatic electrophilic substitution or electrophilic aromatic substitution reactions. Then we'll go right into a new type of substitution reactions called the acylation. Notice this is acylation compared to alkylation, which we did earlier. Next, we'll do another type reaction called the sulfonation of benzene, and we'll demonstrate the importance of sulfonating a benzene ring. Then we will concentrate on the reactions of substituted benzenes. So in other words, if we have a substituted benzene and there is a reaction, what will be the product of that substituted benzene? Then lastly, we'll look at the substitution of polycyclic aromatic compounds, in particular naphthalene. So let's begin. As a quick review, you will recall that the electrophilic aromatic substitution reaction involves of course, an aromatic system. That's why it's called aromatic substitution. Then it involves a hydrogen being replaced by an electrophile to give a substituted benzene. Of course, this lecture here concentrates on benzene because it is the classic example of an aromatic molecule. Just a reminder, a catalyst is always needed. Why? Because benzene is a very stable molecule. Remember, it has 36 kcals of resonance energy compared to a hypothetical cyclohexatriene. So it's very stable. So don't forget your catalyst. Always use a catalyst whenever we're doing an electrophilic aromatic substitution. To remind you, remember, an electrophile is an electron-loving species. Electron-loving species, which means that it's really E+. Last lecture, we looked at the nitration, how to put on a nitro group on a benzene, and here is the active reagent, and here's the catalyst. We also looked at putting on a bromination of benzene. Here's the active reagent, and here is the catalyst here. We also looked at putting on a chlorine on the benzene ring, and here is the catalyst. And lastly, we looked at the alkylation, putting on an alkyl group R, or a carbon-containing alkyl group with a catalyst, aluminum trichloride. And of course, that reaction was discovered by Friedel and Crafts, and now it's known as the Friedel Crafts alkylation reaction right here. Let us look at today's lecture. So what we'll do here is we will be concentrating on the acylation. Remember, the acyl group is right here. The acylation on benzene. So let's look at the acyl compound first, just generally. So here's the carbon-oxygen double bond, and here's the R group. Equally important, here is the leaving group. Of course, as we have discussed, the leaving group could be a chloride. It typically is, but it doesn't have to be. We just need a good leaving group here. We'll need a catalyst. Of course, as we have seen in the previous lecture, the catalyst is basically here to break this bond, to liberate the electrophile right here. So here's the leaving group, typically a good leaving group, and that's typically your chlorine, as we've said. Equally important, though, is the product is a ketone. Carbon-oxygen double bond with the benzene ring on one side and an alkyl group on the other side, depending on this alkyl group here. Classic example is shown here. So here's benzene. Here's an acid chloride. This one is 1,2,3-propanol chloride. Catalyst, don't forget your catalyst. Carry out the reaction, you get a ketone where this group here is now being substituted for this hydrogen here, and here it is right here. And of course we have the Cl as the leaving group, and of course there's an H coming off, so the product here is HCl as the inorganic product. Let us look at the mechanism though, so we can make sure we understand what's happening here. So here's the general reaction again. R, alkyl containing group, carbon containing alkyl group, and an acid chloride. Catalyst. Here's the catalyst, AlCl3. It has a vacant orbital. Notice here, vacant. And the importance of that is that it's now pulling these electrons from the chlorine to form this bond right here and making this even more electrophilic. So once this comes off as AlCl4 right here, negative, we have what's generated here as the acyl cation. Acyl, notice it's not a carbocation. It's called an acyl cation. Why do we stress that? Because it is very stable, as illustrated here from the resonance structure. Here's one resonance structure. We can pull these electrons in to neutralize that positive charge and move it over to here. So that's another resonance structure. So the acyl cation is very stable. It will react with the benzene. So let's take 2 electrons from the aromatic ring and form a bond to this carbon right here. And here it is. If we take these electrons out, this carbon here is now positive. So that's the benzenium intermediate. As we have demonstrated before, this intermediate here is stable, relatively stable, should I say. And this step is called the RDS. Why? Because we are destroying the aromaticity of benzene, which is very stable, to form an intermediate. As you can imagine, that is a slow step, a very reluctant step, the rate determining step. Since we have an intermediate, it will go on to form the product, which means just a loss of this proton, leaving these electrons here to form this double bond, and this is again aromatic. And since it's aromatic, that's a stable product, and this becomes a fast step. Bottom line is we have now generated a ketone as the product. So here's some examples of the Friedel Crafts acylation. Notice the name again. It's the same 2 chemists who discovered the Friedel Crafts alkylation, also discovered the Friedel Crafts acylation. So we can take benzene. Here's our acid chloride. Here's our catalyst right here. Here is our leaving group. So as you can imagine here, the other product is HCl. And what we're doing here is we substituting this hydrogen for all of this right here, and here it is. So again, you should be able to predict the product given benzene and the acid chloride and the catalyst. Same here. Let us look at a practical application of the acylation reaction. You will recall that the reaction of benzene with this alkyl chloride, 1, 2, 3, that's chloropropane, If you carry out this reaction in the presence of a catalyst, there will be a reaction. The problem is, though, is that since a carbocation is the intermediate, we have possibility of rearrangement, so there are two possible products. This is the expected product, and this is the unexpected product, which I'm pretty sure will be the major product because it's coming from the more stable carbocation, the secondary, compared to the primary. So if your job was to make this as your product, the first day on the job as a chemist is to produce a large quantity of here propylbenzene. How do you do it? You would not use this reaction. Why? Because the yield, percent yield, is extremely low. But here's a way around it, a workaround. If you do an acylation, a Friedel Crafts acylation, you'll get this as the only product, the ketone. All the difference between this ketone and the product here is the carbonyl. You may recall, or you should recall, that a carbonyl can be reduced to here a CH2, a methylene unit, using, for example, the Wolff-Kishner reagent or reaction, or the Clemmensen reduction, or any other good reduction reaction that we have studied. So here we've made this practically 100%, or pretty close to 100%, by this route here, using the acylation followed by a reduction, compared to this route here, which is not a good route for making that product. So again, this gives you an appreciation for manipulation of the various chemistry and type reactions that we have studied. Let us look at another type reaction here, the sulfonation of benzene. So here's benzene, here's sulfur trioxide. As you can tell, the sulfur here is very electrophilic based on this positive charge right here. In the presence of an acid, as you can imagine, a catalyst here again. So here's a catalyst. We'll have a substitution reaction where this H is now substituted for this to give this as the product. So for the sulfur trioxide here in the catalyst, this is our active electrophile. So let's look at the mechanism. As same mechanism as we have seen before. These electrons take 2 electrons from our benzene ring. Remember, we have 6 here. 6 electrons in benzene. So let's take 2 and form a bond right here to this sulfur, which means that what's left behind is a positive right here. This is, of course, your resonance stabilized intermediate. Fairly stable, but not as stable as benzene. So therefore, this is the rate determining step. In the fast step, as you can imagine, we lose a proton. The catalyst is regenerated, and we have here our sulfonated benzene. Okay, I'll come back to that in a second to give you an application of that. But let's move on into another aspect here. The electrophilic aromatic substitution of a substituted benzene. So here we have a substituted benzene, has a substituent here of X, substituted benzene, which has X here. And if we react this with our electrophiles, same electrophiles that we have been reacting before, in this case you will not get just one product. As you'll see here, there's a possibility of 3 products, because we can put the substituent here, the E, we can put it here, or it can go here, or it can go here. Just to refresh your memory of the different position, this is the ortho position, this is the meta position, and this is the para position. So we have 3 possible products if we are reacting not benzene but a substituted benzene with an electrophile. Now comes the question, which is the major product? Because as you can imagine, one will be the major product and the others will be the minor product. Which is the major product? Let us see. So first of all, we'll have to analyze the X, the atom that's directly bonded to the benzene ring. First, if there is a pair of electrons on that atom, key here, a pair of electrons on this atom here, let's look at the possibility. There are resonance structures here where these electrons can be donated in the ring, making here negative, ortho position, and here the para position negative. So we say that these pair of electrons are activating the ring, making it more negative here and here. Of course, this is the same position as over here. So it's activating the ring, making it more nucleophilic. So you can see if this is reacting with an E plus, you can imagine where it would go. E plus, being positive, would prefer to go where the negatives are. So let's see. So here is anisole or methoxy benzene. The O is bonded directly to the benzene ring, and here's a pair of electrons. It has two pairs, but it just needs one pair of electrons. So one pair here will activate the ring, making these positions here more negative. Here's our electrophile right here. This is the electrophilic carbon. Here's our leaving group. Here's our catalyst. So after the reaction is done, you should get two products with the substitution in the para position and the meta position. Notice that we're writing here this as the major product and this as the minor product. Why? Looking at this product here, you can see that this group is pretty close to this group, so therefore there is steric interaction or steric crowding. Because as I mentioned earlier, if two groups in chemistry or in a molecule get too close together, it's not a very stable situation. So putting it in the para position makes it further from each other. Therefore, this is the major product. So whenever we have a molecule, a substituted benzene, which has an atom that has a pair of electrons, and there's an electrophilic substitution, the major product is always the para product. Okay, let us look at a reaction here. Here is another example. This one is the methyl substituent. Notice there are no electrons here on this carbon. So the question now is, what is the major product if we react toluene or methyl benzene with an acid chloride in the presence of aluminum trichloride, the catalyst, or the Friedel Crafts acylation reaction? The bottom line is that alkyl groups are considered electron releasing. So it will activate the ortho and the para positions, or the ortho positions and the para position. So we would expect again, if there's an alkyl group here R, where methyl is an example, this will be the major product, and this is the minor product again due to steric interaction between these two groups here. So the major product is the para product. So if you're asked to predict the major organic product, this is it. This is the minor one. So you would not write that as the organic product. And of course, this is the inorganic product. So that's not required in writing the structure of the major organic product. Let us go back to the sulfonation. We mentioned that it's of practical use here. So if we have this molecule here, and we need to make this as our product. So we're going from methylbenzene toluene to 2-chlorobenzene. Notice there's no substitution here. So what we can do is the sulfonyl group is a protecting group, or can serve as a protecting group. So we can put it on. Notice, because this is an OP director or a para director, it's going to direct this incoming substituent here. If we carry out a reaction with chlorine, or the chlorination of this aromatic compound, since this is now a OP director and this position is blocked, it will put it in the ortho position. And of course, since this is a reversible reaction, we can take this off by using an excess of acid here to get this as our major product. So that's a practical application of the sulfonation of benzene. It can be used to block a position here, carry out another reaction to put a substituent over here, and then take it off after we're done. Let us look at another type substituent adjacent to the ring. In this case, this is X, but this X does not have a pair of electrons. Notice when we said that the methoxy has a pair of electrons, but this one does not have a pair of electrons. What it has, however, is a double bond that's adjacent to the ring and an electronegative atom Y. What that does is it takes electrons from the ring. So the resonance structures will show that electrons are now coming from the ring and going onto our electronegative atom Y. As you can see from the resonance structures, this position is positive. The ortho, this position, the para, is positive. This position, the ortho, is positive. So, as you can imagine, if we were to react this with E plus, an electrophile, it would not go here, it would not go here, it would not go here, because they have the same charge. And we say like charges will repel each other. So by default, you can expect it to go here. As you can imagine, this type substituted benzene is not as reactive as the one that has the electron pair right here. So we say that this is a deactivating as opposed to an activating group for benzene. So let's look at the mechanism or reaction here. So here's a group, the nitro group. We know how to make nitrobenzene. You draw out the lowest dot structure. You will see that here is a double bond that's adjacent to the phenyl ring or the benzene ring. Oxygen is, of course, electronegative and more electronegative than nitrogen, so it's pulling the electrons from the ring onto the oxygen. You can draw the resonance structures and you'll see that the positive charges will be here, here, and here. So by default, if you react this with an electrophile, an acid chloride, using the Friedel Crafts acylation in the presence of a catalyst, the reaction will go not as quickly as the others to give here the meta product as the major and only product, as the major product. So this is the reaction. Summary: these type substituents here are called meta-directors. The other one is called a para-director. Why para? Because it directs the incoming group into the para position. Why meta-director? Because these type substituents direct the incoming electrophile into the para position. So it's called the meta position. Let me say that again so you're not confused. This type substituent here which has a double bond adjacent to the ring, directs the incoming electrophile into the meta position. Hence it's called a meta-director. Let's look at an example here. So if you had here benzoic acid, an analysis shows that this is a double bond adjacent to the ring. So therefore this substituent here is a meta-director. So if it's a meta-director, here's our electrophile, E plus here. And you should know that this is really the electrophile here. And of course the HCl is the other inorganic product. But the bottom line is, here's a catalyst. It will direct it into the meta position. So here's the major product of this reaction. Let us see if we can apply what we've just learned. We've learned of the ortho para-director. We've learned of the meta-director and how to identify them. And we've also learned of the, excuse me, the Friedel Crafts alkylation and acylation reactions. So, starting with benzene. Of course, you know why we start with benzene, because it's fairly common. It's easy to get from fossil fuel based on the distillation of petroleum products. So we can get benzene fairly easily and fairly cheaply. This is the Friedel Crafts alkylation. This one works because it's just a methyl group, so therefore there's no rearrangement. So we have here methyl benzene. Notice this is now a para-director. So if this is reacting with the acid chloride here, where that's the electrophilic carbon and a catalyst, this will be our major product. But if you should change the sequence of reactions as shown here, so in this case, same starting material, benzene, but do the Friedel Crafts acylation this time, reacting the acid chloride with the benzene in the catalyst, we get this group. This group here is now a meta-director, and if we should do the Friedel Crafts alkylation, this will be the major product. So you know where we're going with this. Synthesis. You can synthesize different molecules or substituted benzene based on the choice of reactions. Let us look at another example here for the application. So benzene, doing the Friedel Crafts alkylation, we get methyl benzene. This is now a para-director. Same reaction, give you this. Here we have potassium permanganate oxidizing agent. I need to point this out. If there is a carbon that has at least one hydrogen in the presence of a strong oxidizing agent, this group will be oxidized to the carboxylic acid. There's more information on that in the text. But the bottom line is, if there's a carbon that's adjacent to the benzene ring that has at least one hydrogen, notice it has to be one hydrogen. Doesn't matter how many alkyl groups or carbons that's contained, but it has to have at least one hydrogen that's bonded to the benzene ring. So this could be R and this could be R. This will go to the carboxylic acid right here in KMNO4. So we can make this molecule here, but look at this. Can we make this molecule here where this is a OP director? This is a meta-director, pardon me. This is a meta-director because of that double bond, and this is a meta-director because of that double bond. Look at this one. This is a meta-director because of this double bond. This is a meta-director because of that double bond. But the relationship here is in the para position. The relationship here is that it's in the meta relationship. So it's just a matter of the sequencing of reactions that we use. So here we can start again with benzene, do the Friedel Crafts alkylation to get methylbenzene. Now we can do the oxidation to get the carboxylic acid, which has a double bond here. So this becomes now a meta-director. So therefore this reaction here, the Friedel Crafts acylation, will put this group in the meta position. So again, you'll have to take your time to fully appreciate the chemistry here, maybe pausing the video at different points and making sure that you understand how to use the reactions to get the products that you desire. Lastly, let us look at naphthalene. So here is naphthalene, a polycyclic aromatic compound. It's aromatic because it here has 10 electrons. So you may recall the test of the characteristic for aromaticity has been proven for this molecule, so therefore it's aromatic. So it will undergo an electrophilic aromatic substitution reaction. So it's illustrated here. But before we look at the products though, the hydrogens here are not all equivalent like they are in benzene. Remember, for benzene here, all the hydrogens are equivalent, but for naphthalene they're not. So we can describe them as alpha and beta. These two hydrogens here are equivalent. So we call them the alpha hydrogen because they're next to the ring fusion. These two hydrogens are equivalent. We call them the alpha hydrogen because they're next to the ring fusion here. So we have 4 hydrogens that are the same and are described as H alpha. We have here 4 hydrogens that are the same but different from the alpha. We describe them as beta because alpha beta, 2 carbons removed from the ring fusion right here. So these 2 hydrogens are different. So in a reaction, in a substitution reaction, we can substitute H alpha to get a product here, or we can substitute H beta to get a substitution product here. 2 possible products. Now comes the question, which is the major organic substitution product? To do that, we'll have to look at the stability of the products. So, if we have a substitution here and here, we will have, so here's a substitution, there is steric interaction between this alpha hydrogen and this substituent here, E, make that not very stable. Over here, however, there is a E where this is now further from this hydrogen and further from this hydrogen, so there's less sterics. So this product here is now more stable than this product. So this is more stable than this product. So again, if you're analyzing the stability of the product, you'd expect this to be the more stable product and hence the major product. But there's another aspect we need to analyze. We need to analyze the stability of the intermediates that are formed. So let's look at this. If E goes to the alpha position, we have here, here's the intermediate. Here we can draw another resonance structure as shown here. So notice this benzene ring here is still intact, so it's pretty stable. If we should put the substitution into the beta position, the positive charge goes here. This double bond here cannot stabilize that positive charge. In other words, this positive charge cannot be localized using this double bond, The only way it can be localized or delocalized is to destroy the aromaticity in here. So let's say that again. By putting the positive charge here, the only way this positive charge can be delocalized is to destroy the aromaticity here, which means losing energy. This double bond over here cannot be used to delocalize this positive charge. Up here, putting the electrophile here means the positive charge is here, so these electrons can be used to delocalize this positive charge over to here. So this is more stable. So putting the substituent in the alpha position generates a more stable intermediate. So we have two concepts here: the stability of the intermediate and the stability of the product. Let's see if we can analyze those two concepts to predict the product. Here's the energy profile for that reaction, or using this concept. So we started with the reactant. We form a intermediate. So this is the less stable intermediate. Notice the higher in energy is less stable. The lower in energy is more stable. Or we can do here the other intermediate to generate a more stable intermediate, lower in energy. And we can get here a product which is less stable because it's higher. And here a product that's more stable. Now it's lower. So we're looking at the relative heights here for the stability of the products and the relative heights here for the stability of the intermediates. So now let us just put in the structures for the intermediates and the products. So this is the structure for the intermediate, putting the substituent or the electrophile in the beta position. Not stable, not as stable, because this charge here is localized and it can only be delocalized by destroying this aromaticity. Putting the electrophile in the alpha position generates a stable intermediate because this charge here can be delocalized using these electrons. So this intermediate here is more stable than this one as illustrated here. Let's look at the product. So this product here is more stable because this electrophile, there's no real steric interaction between these hydrogens, whereas this product here is not as stable because there is steric interaction with that hydrogen. So what that means is, let's concentrate on this for another minute. So this represents here the energy of activation. So notice the energy of activation to give this intermediate is less, which means a faster reaction, than the energy of activation here to give the less stable intermediate, slower reaction. Over here, this product here is now more stable and this is less stable. So if you wanted to produce this as your product, this one here, you run your reaction at a low temperature so that we just have enough energy to meet this energy of activation here. Low temperature. Just the minimum amount of energy required just to get up to here so it can go on to give this product. If you want this product here, you get the reaction to a high temperature so it gets all the way up to here. Supply enough energy of activation here to get to this and over to this intermediate. So in the fast step, we will get this as our major product. So let us look at the summary. So if you have naphthalene here, run the reaction, or the sulfonation in this case, at a low temperature. There's just enough energy to get to the more stable intermediate. And then that goes on to give the product. We call that the kinetic product, because that's the product that results from a low temperature, meaning that you just supply enough energy to get to the energy of activation for the more stable intermediate. On the other hand, if you run the same reaction but at a high temperature, so you are supplying enough energy to get to the less stable intermediate. The less stable intermediate, a lot of energy, high temperature. So you get to the less stable intermediate, that goes on to form the less stable product here. The more stable product here called the thermodynamic product. Let me say that again so not to confuse you. So if you run the reaction at a high temperature, there's enough energy to get to the intermediate that is not stable, not as stable, right? So in other words, you've surpassed the energy of activation for the most stable intermediate and gotten to the energy of activation for the less stable intermediate, because there's lots of energy right here. That quickly goes on to form the more stable product, which is also called the thermodynamic product. I think that's the end, and that's the end of this lecture for chapter 17. So please go ahead and read about this chapter here. We have one more lecture on chapter 17. As you can see, it's a lot of material. So you may have to go slowly through this, through the slides and the PowerPoints, and just to make sure that you understand this material. The tutorial set is designed to get you to apply this material here. So take your time and work through those very carefully, and make sure you understand the concept and can apply it. And as I keep reminding you, we're here not only to learn the facts, the content of organic chemistry, but equally important, to use the reactions to solve problems. Use the concept of the reactions to become better thinkers and better problem solvers. Okay?